So let's read the question and identify what we do know, right? Miles goes travel along Lake Street at 15 meters per second. Miles accelerates at let's say feet per second squared.
Yeah.
Let's get rid of that. Let's make it meters. That's really going to complicate things, isn't it? Okay, so we know the acceleration is 2, right? But this 15, like what is that? Well, it's a velocity, but is it an initial velocity? Is it a final velocity? Is it an average velocity? Is it a change of velocity? It's the initial. It's how fast he's going to begin with, and then he speeds up. Right? So that is the VI. Determine the distance traveled by Miles in 12 seconds. So our time is 12, and the distance traveled we're solving for D. Now right away, grade 11 students should recognize, oh, I'm looking for the displacement. To find it, the only one that I can use that I have in my toolbox is the one with V bar in it. Do I have the average velocity? You do not. Many of you just did this. Many of you just put 15 and 2 and got 30. Okay? But that is not the average velocity. That's how fast he was going at the start, and then he speeded up. So he's going to go farther or less. He's going to go farther, right? Because he's going faster. Okay, so if you want to work backwards, some students do find this a good strategy. I'm going to solve for D there. I know the T, I need to find average velocity. What's the other formula with average velocity in it? V bar equals VI plus VF over 2. And you'll notice how I'm going from right to left now. I know the initial velocity, but I don't know the final. Is there another formula that has final in it? Yeah, there is. There's one that has delta V is VF minus VI in it, isn't there?
Yeah.
And I got the VI, but I don't have the change of velocity. So what's the other formula that's got change of velocity in it? Well, it's A equals delta V over delta T. And that one I have two things. You see how I sort of made your plan by going backwards from right to left? See how writing the formula is a valuable thing to do? It's not wasting time. Trust me, you guys waste plenty of time. Writing formulas is not a waste of your time. Okay, so what is the acceleration? 2. We're going to solve for change in velocity. And the time is 12. So we got 24 meters per second. That, again, is how much the velocity changes. Right? How much it changes. And now I can put that in there, right? So I'm going to put 24 is equal to VF. The VI is 15. We're going to use our math solving skills. I need to make a little more room here. Can I do this? Is that okay? I realize you can't do that. So the 15 goes to the other side, becomes positive. 24 and 15 is going to be 39. That's moving fast. Now that I got that, the average velocity is going to be 15 plus 39 over 2. Well, 15 plus 40 is 55. So one less than that is 54, right? 54 over 2, which is 50 divided by 2 is 25, and 4 divided by 2 is 2. 25 and 2 is 27. (27) is equal to D over 12. Instead of 12 times 27, we had 10 times 27, that would be 270. 2 times 27 we know is 54. So I got to add 54 and 270. Oh, can I do that in my head? 224. 324, right. 324. Of course, you can use your calculator. I expect you to do it in your head. How many marks do you think? The key thing is to recognize that you do not have the average velocity. If you just go ahead and plug in 15 times 12, you've only done one step. You're going to get 1 out of 4. Okay? Make sure you are, when you use average velocity, make sure that that is actually something that you can use. Oh, yeah? Oh, you're right. So you would have to actually do that first, right? Yeah. I think I just cut and paste something from an old one. So it is right there. It'd be the 39, yeah. Yeah. This is what I expect you to be able to do on the next test, like the one that's happening in 2.5 weeks, right? Not tomorrow, it's the one that's happening in a while. So you need to identify the 4 fundamental forces of nature, which we will cover today. Perform an experiment to demonstrate Newton's second law. Define the unit of force as a Newton. That's pretty easy. All you have to do is say a Newton is the unit of force, and then you're done. Define F net as the vector sum of all forces acting on a body, or in other words, know that and be able to apply it. Construct free body diagrams to determine the net force of various objects, including balanced and unbalanced forces. And the big one, solve problems using Newton's second law, F net equals Ma, and the kinematics equation. So we're going to take all the kinematics equations that we've just done in the last week, it's going to be tested on tomorrow. We're going to take it a step further and include F equals Ma in there as well. And these are the types of problems you're going to see in the next few weeks. Horizontal force with friction. So where you got a force one way, friction the other. You might have a force at an angle, like so, like someone pulling on a sled. Right? Or you might have perpendicular forces, a top-down kind of thing, both with and without friction. So we can look forward to those kind of problems. You can check them off as you're going along, if you wish. Okay, so now let's talk about fundamental forces. All right, so these are like actual notes in that traditional sense. But as always, if you think that you're going to do better by just sitting back and listen, you go right ahead. If you want to summarize the notes, you go right ahead. If you want to write everything that I have on the screen down, I strongly suggest you don't. Okay? They are more than anything speaking reminders for me to say something. Okay? So don't feel you have to write everything down. I'll let you get yourself ready. When I say the word fundamental, what does that mean to you? What does the word fundamental mean, Anna? Okay? It's like you need it. Like a fundamental course, like not something that's required. You're on the right track, yeah. Fundamental usually means like basic or something that everything else is derived from. But you're not entirely wrong with me. Okay, so there are 4 fundamental forces. I will tell you about all 4 of them. The first one is gravity, gravitational forces. It's an attractive force. It's a good-looking force. Thank you. I'll try not to let it get you down. You see this pencil sharpener right here? I'm attracted to it. No? Are you attracted to it, Jason?
Hard no.
Pardon me?
Hard no.
Hard no. See, you're wrong. You are attracted to the pencil sharpener. Just not as much as me. How come I'm more attracted to the pencil sharpener than Jason? Because I'm much, much closer. Jason's more attracted to, say, the cart of laptops over there. It's an attractive force that exists between all objects, including people. Okay? And the gravitational force between the center of the Earth and objects near it causes objects to fall toward the surface of the Earth. If I get my angry Pac-Man foam ball, and I drop it, and we all know what's going to happen, right? Forget about the bent over part. It's going to fall because it's attracted to the Earth. But is the Earth attracted to the foam ball? No? Maybe, she says now, after she reads my face. What do you say, Jason? Is the Earth attracted to the angry Pac-Man foam ball?
I'm guessing yes.
You're guessing yes. Why? Because I gave Mallory a hard stare? Or you just... Well, gravitational force between the center of the Earth and objects near it causes objects to fall towards the Earth, right? The Earth is an object. Is the Earth attracted to the Pac-Man foam ball? The answer is yes! More on that later. Okay? When we get into gravitational fields, right? Anything, anywhere on the Earth is attractive. I remember a young person said to me once, we were talking about gravity and stuff, and they said to me, how come people in Australia don't fall off? There's Crocodile Dundee. Right? They're underneath there, right? It's the bottom. How come they don't fall off? Gravity. Right? Isn't that kind of weird to think about? There's people on the other side of the Earth that are like literally upside down, walking around. Maybe we are. Yeah. Good point. The second one is, oh, I always forget to do this. Oh, I was going to get the screen shade, but I can't find it. You don't like the screen shade? See, I like it because then I can control what you're going to be writing. I really want it. Doesn't want me to do it. Electromagnetic force is the force that holds matter together. It is literally holding you together right now. It provides the force that binds atoms into molecules. Right? So, like, for example, Kelly's got a water bottle here. It's made of water. There's water in it, right? It's got hydrogen and oxygen in there. The electromagnetic force is holding the water, the hydrogen, and the oxygen atoms together into water molecules, thankfully. Otherwise, we'd have a flammable gas sitting there, right? We don't want that. It is the force between particles of opposite charge, and it is attractive. It's what you guys all know. You learned it in grade 9. You know that positive things are attracted to negative things. Sometimes that's true with humans, too. Watch out for that, by the way. Don't you be attracted to negative people. But the force between particles of the same charge is repulsive. Positive and positive don't like each other. Neither do negatives and negatives. Okay? That whole force is known as the electromagnetic force. These are fundamental. And when I say fundamental, I mean that all other forces are derivatives of these four. They are combinations and such. Or just rewordings, renamings, relabelings. Okay? So again, this is the force between atoms that either hold them together. If it's two negatives, like push them apart. Do you need the pictures, do you think? It's up to you. I see a couple people still writing, so I'm just going to pause. Good, ladies? Yeah? People let me go to this. Okay, so here's a question for you. Since like charges repel one another, positives don't like each other, how can positively charged protons exist closely packed in an atomic nucleus? You don't need to write that question down. Just think about it. Say, for example, fluorine. It's got 9 electrons, 9 protons. Atomic number 9. It's got 9 protons. Where are those 9 protons located? Packed densely in the nucleus. Well, I thought positives, you ever thought about that? Positives don't like each other. How can you have 9 positive protons stuck in the nucleus? Well, it turns out there's another force called the strong nuclear force. And it holds protons and neutrons together in atomic nuclei. and it is the strongest force, strongest of the fundamentals. But it acts only very, 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 very short distances. That is the strong nuclear force.